Not all instructions write registers. So this policy that we have just discussed is inaccurate. Sometimes it would forward when it should not. So let's take an example here. In this immediate R type instruction, you see that add I x0. So whatever operation that we are performing, it is writing into x0, but it does not make any sense because x0, the contents of x0 will always remain 0, and we have seen this example in when we want to perform certain operation, or we want to do not perform any operation, so we write just results back into the x0 register. So here you can see this, according to the policy, the conditions that we have discussed, the RD is equivalent to the RS1 in for the next instruction. So according to the policy that we have just developed, it will still forward the value, so, which does not make any sense. So we do not need to forward. So what we need to do is to forward only if the RD for that instruction is not x0. So before forwarding, in the policy that we have just discussed, we need to update the policy to incorporate these changes. Like we have to also check, first of all, we need to check if the register RD is not equivalent to 0, which means it is not x0. And both in this both phases, both stages, like xmem pipeline register and mem write back pipeline register. The second thing is that we need to determine if the instruction will write to a register by checking the reg write signal. So sometimes, like LW instruction, it write to the register, right? But there is SW instruction also, which does not write to register. Okay, so we need to check if the register write signal is set for that particular instruction or not. Why do we need to check the reg write signal? So let me take you an example, give you an example here on the whiteboard. So here, suppose these are the two instructions. So do you think there is any data dependency here? Give a pause and see if there is any data dependency here. Let's say this is not x2, maybe this is x3, just to be more clear. By the way, even if it is x2, there is no, and this is considered as the rs1, and this is considered as rs2 in the case of SW instruction, okay? And this is again, this RD. So data dependency is when the current instruction, the RD of the current instruction, is equivalent to one of the source register of the next instruction, which means that this instruction is writing something which is being used by the next instruction. So that is what we call the data dependency. So here there is no data dependency, but give a pause and ask yourself if there is any data dependency. All right, so if your answer is no, then try to check or decode this value. For example, we call the instruction encoding format. So we have the instruction encoding format as opcode, and then generally what we have is the RD comes here, and then func3 comes here, and then rs1, rs2, and then it contains the func7 field, right? For the SW, what we have is the same format, the opcode, but in SW there is no RD. So what we have here is the immediate data and the first 5 bits of the immediate data. Okay, similarly then we have func3, and then we have rs1 and rs2, and then the remaining 7 bits of the immediate data. So from 0 to 4 and 5 to 11. Okay, so if you decode this 40 in binary, so the binary value of 40 is, you would write 32, set the bit 32, and then 16 is off, and 32 and 8, and then 0 0 0. Yeah, so 1 2 3 4 5 6. So this is 1 2 4 8 16 32 6, and then 7 8 9 10 11 12. Okay, so this is the binary equivalent of 40. Now how does this thing is split into this format? So these are the 5 bits, that will go here, right? 0, 1, 2, 3, and 4, and the remaining 5 bits, sorry, remaining 7 bits goes here. Now in the processor diagram, you see what is this value equivalent to? If this value is stored here, what is this value equivalent to? If you look at this value, it is 0, 1, 0, 0, 0, which is equivalent to 8, right? So if you look at the processor diagram when the instruction is decoded, so this is instruction memory, and what we have is the register file, and how the instruction is decoded, it goes into the rs1, rs2, and then rd. Okay, so it goes here and this. So what are these wires? So these are the 5-bit wires, which are actually the same thing here. All these 5 bits are tied together and wired to this line. Similarly for rs2, these 5 lines are tied together to this line. For rd here also, let me choose another color, say purple. So these five bits are also tied to here. So even if the instruction does not have rd, this value, these 5 lines, will be tied here. And currently in this SW instruction we have the value 0, 1, 0, 0, 0, which is 8. So it will treat this instruction, it will consider as our value of rd to be 8. So this is the first instruction. So look at here, in this instruction it will consider this rd equals x8, and here in this instruction we have rs1 equivalent to x8. So it will consider this as a data dependency, because the rd in this instruction is equivalent to the rs1 in the next instruction. So it will treat it as a data dependency and may try to forward from the wrong pipeline register. But the SW instruction, in the SW instruction, does it write to the register? Does it write to the register file? No. So in this SW instruction, the read write signal is 0, because the SW instruction does not write any data into the register file. Okay, so this is why it is important to check this this control signal. Okay, like after explaining this, we have to update the pipeline architecture, the hardware of the pipeline architecture. So we need to check whether the destination register is 0. If it is 0, we do not need to forward it, and we also need to check the read write signals. Okay, so the updated data path for the pipeline register would have something in between, some components in between. And you know that in this instruction we need to decide whether the data should be coming from the register file, or the data should be coming from xmem register, the pipeline register, or it could be coming from the mem write back register. Okay, so in that case there are 3 incoming data sources for this ALU. So we have to select one of them from the 3 incoming source of data, and we can simply insert a mux for both of the input of the ALUs. Okay, so this is the ALU input. The first of the input, it will decide if there is no forwarding. We need to decide whether the data should be coming from the register file, or it should be coming from the xmem phase or the mem write back phase. So this forwarding unit will be checking those conditions. Okay. So it will, because there are 3 input sources in the mux, so the forward A signal or forward B signal, which is the select signal, it should be 2 bits wide, because if it would be 1 bit, then it could either select this input, maybe 0, and or it could select 1 value. It cannot select the value 2 here. So in order to select more than 2 inputs in a mux, we need to have these select signals more than 1 bit wide. In this case we need 2 bits. So if you look at this condition here, let's say 0 corresponds to the data coming from the register file, 1 corresponds to the data, so when the when the forward A signal, which is the select signal for this mux, if it is 1, then data must be coming from the mem write back phase. If it is 2, then the data must be coming from the xmem phase, xmem register. And if it is 0, then it should directly be coming from the register file. And if you look at here, so when the mux is 0, when the forward A is 0, it will directly fetch the data from the IDX, which contains the data fetched from the register file. Okay, when the forward A signal is 1, you see, follow this path, and you see the data is coming from the write back register, mem write back register. If the value of forward A signal is 2, then you can see the data is coming from the xmem register. Okay, so same is the case with the forward B signal, the another input of the ALU. Okay, so the updated conditions now are here. The policy is updated for the hazard in the execution phase. We first check whether the read write signal is high for the xmem, which signifies that the instruction will be writing the data into a destination register, into a register file. Okay, so once we assure that the instruction is writing the into a register file, then we check if the RD of that instruction is not equivalent to 0, which is not x0. And then this is the same condition which we have studied in the previous slide, that if the register RD in the execution and mem register, pipeline register, is equivalent to register RS1 sitting in the IDX pipeline register. When this is the case, then we have to forward the data from which is 10, it's a binary 10, which corresponds to 2. We have to forward the data from xmem phase. Okay, same is the case for checking the RS2 condition. So in both the cases, if the RD is equivalent to either RS1 or RS2 sitting in this register, we have to set the value of the forward A and forward B to 2, which will be forwarding data from the xmem register to the ALU. Similarly, if the instruction is in the write back phase, mem write back phase, so we will follow the same thing. We check whether the instruction is writing into the register. If it is not equivalent to x0, and then the register's RD is sitting in the mem write back phase, mem write back pipeline register is equivalent to either RS1 or RS2. In that case, we have to forward the data from the mem write back register. We have to forward the data from the mem write back register. Okay.